Nowadays, we understand the nature of the universe and its components to an unprecedented level of detail. Scientific evidence tells us that if we could gather all the ordinary matter content in the universe, gas, planets, stars, galaxies, it would account for only about 15% of the total, while 85% is believed to be of a mysterious nature and is referred to as dark matter. The first indication for the existence of dark matter came in 1933. Astronomer Fritz Zwicky coined the term to describe an invisible matter whose presence he deemed necessary to explain galaxy motions in a large galaxy cluster.
Dark matter is observed in many ways, but a simple way to understand why we think it exists is if you look out on a starry night, we see that there must be much more mass in the space between the stars as in the stars themselves, or else the stars would not be held into the pattern that makes up our Milky Way galaxy. The gravity created by this 5 times greater amount of mass is what's necessary to hold the galaxy in its current shape.
Clearer proof came decades later from several sets of astronomical observations. For instance, the rotational behavior of spiral galaxies such as our Milky Way is proof of the existence of dark matter. If a large spiral galaxy consisted solely of atoms, the ordinary visible matter, the inner stars would rotate at a higher speed than the outer ones. This would be seen clearly in the rotational velocity plot. However, from rotation velocity astronomical measurements, we see a different behavior. The outer stars rotate around the galactic center as fast, if not faster, than the inner ones. This can only be physically possible if the galaxy itself is immersed in a much bigger and massive halo of a dark matter we can't see, with a total mass about 6 times larger than the ordinary visible matter. Scientists have been producing theories on possible dark matter candidates for decades. Among the leading candidates, motivated by the so-called supersymmetry theory, are WIMPs, weakly interacting massive particles, that only interact with atoms through gravity or through very rare collisions. We could, in principle, observe these collisions in detectors with very large target masses, 1 to 100 tons, located in deep underground sites to eliminate particle background. The Darkside 20K collaboration is an international affiliation of over 60 universities and research institutes from around the world that aims at the direct detection of WIMPs at the Gran Sasso National Laboratory in Acerci, Italy. The target material in Darkside 20K is liquid argon, a cryogenic material with optimal properties for a dark matter experiment.
We are using 50 tons of total volume of underground argon. The only way to make it compact, small enough, so we have to do in a liquid phase, so with argon liquefied in the gas phase. That's why we need a cryogenic environment.
The collision between a WIMP and an argon nucleus would produce a trail of free electrons and photon emissions that Darkside 20K would be able to detect.
Liquid argon is one of the best elements for the possible discovery of dark matter. The response of liquid argon to ionizing track is a very strong pulse of scintillation, light particles, photons. The time shape of emission of these photons depends very strongly on the density of ionization. One can thus discriminate minimum ionizing events, which are typically originated by background radioactivity, which we are not interested in, from nuclear recoils, which are the possible signal resulting from the interaction of dark matter on an argon nucleus.
Argon is a gas present in the atmosphere. However, not all argon is the same. Argon-40, with 40 protons and neutrons in its nucleus, is stable and optimal for a dark matter experiment. unlike argon-39, produced in small quantities in the atmosphere by interaction with cosmic rays coming from space. This is why the Darkside 20K target argon is extracted at the Urania plant from the gas coming from a deep underground well in Colorado. Located there for thousands of years, the stable argon-40 is shielded from the cosmic rays, while the argon-39 has had the time to vanish almost entirely by decaying. The underground argon is then sent for further purification to the Aria laboratory at the Ceruci mines in Sardinia, before its use in the experiment.
Underground is a big theme of dark matter research. You need to go underground to detect dark matter. You need to go underground to collect the argon that is required for observing dark matter, because underground the argon is protected by cosmic rays. You need to go underground to purify the argon. You need a very tall mine shaft to host the Aria distillation column. You also need to go underground to host the detector, Darkside. It needs also protection, very strong protection from cosmic rays.
The production of the extremely sophisticated instrumentation for Darkside 20K takes place in several labs around the world. Researchers from the cryogenics laboratory of INFN in Naples, Italy, test the delicate photon detectors, the so-called silicon photomultipliers, or SIPM.
We're going to test and fully characterize more than 10,000 photon detector modules for Darkside 20K. This will happen in this laboratory on a 24 hours a day scale for 1 year and requires a huge automatic facility, and in particular this is done in Naples because of the present laboratory, which you can see is a clean room, a very special clean room, a radon-free one, a unique infrastructure in the world.
We have been using photomultipliers to detect light in particle and astroparticle experiment for several tens of years. Nevertheless, their use in cryogenic liquid detector is challenging. These devices do not like to work at low temperature, and the amount of radioactivity cannot be neglected. On the contrary, silicon PM give their best at low temperature. For instance, the dark rate gets very low when you go at cryogenic temperature, and silicon is a clean material, so they are very suited for low background experiment.
SIPMs are one of the key enabling technologies for large-scale liquid argon-based dark matter experiments, and are produced and assembled at NOA, Nuova Officina Esergi, in Abruzzo. The local governments of the Italian regions of Sardinia and Abruzzo gave a crucial financial and political contribution to the development of the research facilities in Ceruci and L'Aquila, with a positive economic and social return for those territories.
Silicon PM technology will have an important impact also in other fields. As an example, in the automotive sector, the LiDAR will dramatically improve the safety of the cars that we will drive in the future. LiDAR is sending light to a target and measuring the characteristic of the reflected light. Silicon PM are super detectors to make this job.
Ultimately, all the highly sophisticated components will converge at the underground Gran Sasso laboratory, where Darkside 20K will be installed and operated starting from 2024. A huge challenge for the experiment is that all components and materials must have the lowest possible level of natural radioactivity to reduce neutron background.
All the parts, the materials which are used in order to build the containers, the detector and the supporting structure are all chosen to be radio pure, completely radio pure, in order to completely eliminate the natural radioactivity backgrounds.
Yeah, I think the most challenging item for developing this detector is threefold: background, background, and background.
The outer structure of Darkside 20K is a large cubical cryostat chamber that contains around 700 tons of liquid argon and acts as a shield from outcoming background particles. Within the cryostat is the veto chamber, which has the crucial task of separating the effects of WIMP argon collisions from background events, such as argon collisions with neutrons produced by cosmic rays and by natural radioactivity, which, although unavoidable, is minimized in all components and materials of the experiment. The inner chamber and the core of the Darkside 20K experiment is the so-called Time Projection Chamber, or TPC. This chamber contains 20 tons of target underground liquid argon, which is viewed by arrays of silicon PM photon detectors. To observe the signal of a WIMP argon collision, the experiment needs to trace with extreme accuracy both the photons and the electrons produced by the impact. Silicon PMs detect with great accuracy the primary scintillation photons produced by a WIMP argon collision, thanks to their high photon detection efficiency and single photon resolution. A WIMP collision also extracts some of the electrons orbiting the argon nucleus. These are detected thanks to the TPC's two-phase configuration, where a small region of gaseous argon lies above the larger volume of liquid underground argon. A uniform electric field is applied to drift the free electrons upward to the surface of the liquid argon. There, another electric field is applied to pull the free electrons into the gaseous argon, where they produce secondary scintillation photons by a process called electroluminescence. When a WIMP collides with an argon nucleus, it produces primary scintillation photons, which are instantly detected by the silicon PMs inside the TPC. This first signal is called S1. The free electrons produced in the collision drift upwards to the surface of the liquid argon and are pulled into the gaseous argon, where they produce secondary scintillation photons, also viewed by the silicon PM arrays. This signal, S2, happens at a later time with respect to the primary scintillation signal, S1. This configuration allows for the WIMP argon events to be accurately localized in 3 dimensions. The delay time between the S1 and S2 signals accurately defines the vertical position of each event with millimeter precision. The distribution of light over the top photodetector array gives the horizontal position with centimeter-like precision. The veto chamber is then used to discriminate real dark matter events from background signals.
We have been looking for dark matter since several years, 20 years. I've been personally working in this subject for 15 years. And we are going with this experiment to fully explore the range of possibility that this dark matter is composed of a WIMP, weakly interacting massive particle. This would be one of maybe the most sensitive experiment in the world. If the WIMP particle exists, we will discover it, for sure.
If we understand the properties of the dark matter particles, seeing how they might fit into theories that go beyond our current knowledge, called the Standard Model, it will be very interesting for fundamental physics, as well as for the way in which dark matter influences how the universe has evolved. So both in particle physics and in cosmology, or the evolution of the universe, there will be new information that constrains theories, and when we find the right theory, gives us a better view of our universe as a whole.
Thanks to Darkside 20K, we will be able to either detect dark matter for the first time or strongly constrain its nature and its properties. The quest for the discovery of this mysterious component of the universe is on.